Okay, well, welcome everyone. Our speaker today is Alexandru Chirvasitu from Buffalo, and he will talk about Epis, monos, and quantum-flavored category theory. Please, Alexandru.
Thank you very much for the invitation and the introduction. I've been getting these, as I was saying at the beginning, I've been getting these notifications for some time now, so it's exciting to be speaking in the seminar. So let me start here with just some general background. It might get a little boring here and there. I'm assuming nobody minds that so much. So I'm going to place myself inside some category that we will specialize in a little bit to categories of interest to non-commutative geometers. But for now, it's just going to be an abstract one. So this is going to be a category C. And in it, I'm going to have some morphism from one object to another. C prime. Let's call it something. It's F. And the talk is mostly about notions of what it means for F to have large image. So here's a question. What does it mean? And these are not notions due to me. They go way back, right? The results of my own just have to do with applications of this. But this is, I'm laying out some background work here that we need. What does it mean for F to be, sorry about that word, and about the handwriting generally, to be onto? It's question mark. Now, of course, surjectivity doesn't make sense as such because the way you write surjectivity for sets, maybe x and x prime are sets and f is a function of sets. You say f is onto if for every x prime and x prime, there is an x in x such that f of x is x prime. So the whole point here, pun not intended, is that we have elements x in x, or points, if you like geometry, but presumably if you like non-commutative geometry, you like geometry too. So sometimes when x is something like a space, we refer to its elements as points. But the whole issue is that in NC geometry, we don't have points. So this doesn't make sense. You can't write this. There are no little x's. I just have the C and the C prime as abstract objects that, again, I will specialize to particular categories in a minute or later. But they don't have any internal structure that I can use. They don't have little x's living inside them. So I have to phrase ontoness, have to phrase surjectivity. And I'm going to put it in quotes because people don't call it surjectivity. For F in terms of just objects and morphisms, or in just arrow theoretic terms. In terms of just, let me erase this, of just arrows, so that it makes sense. So it makes sense in arbitrary categories. Yeah, so that's the starting point for this, from which we will then veer off into more specific problems. And how you do this is not unique. There's not a unique solution to this problem. There are many, but sort of the most basic one is the notion of epimorphism. So one solution to this problem I posed. Epimorphisms. And the epimorphisms are the epis of the talk's title. Sometimes instead of saying all of this, it's a bit long, people just say epi. Yeah, so when I talk about epis, I mean these guys. So let me just define what these are. So you say that an arrow C is epic or epimorphic. An arrow F, sorry, from C to C prime is epic, or an epi if now you want to take something that's true of surjective functions, but which is nevertheless phrasable only in terms of arrows, and transport it here. And one property that characterizes surjectivity for functions between sets is the following. Whenever I give you two distinct arrows that follow up from C prime into C double prime, so for every G different from H that go from C prime to some C double prime, comma, the compositions are also different. GF is different from HF. So in other words, if you want to capture the intuition of what this says, it doesn't make sense as such because we don't have anything like domains or codomains in arbitrary categories. But if you want to capture the intuition, this says that if G and H disagree on their domain C prime, they already disagree on the image of F. So this is like saying that the image of F is all of C prime, even though we don't have a notion of image. Yeah, so that's why this is a good imitation of the concept of surjectivity. So this makes sense for arbitrary morphisms in arbitrary categories. So this is the analog of surjectivity for arbitrary morphisms in arbitrary categories. Any questions so far? It would be a good point to ask, as I've just finished the definition. And if not, of course, you can stop me anytime. Okay, so with that in hand, let me go back to something the abstract said. I said I would take as my starting point, I mean, apart from from background concepts, I would take as my starting point work by Bien and Borel. Bien and Borel, who were interested in epimorphisms. So now we know what those mean. Epimorphisms in the category. So now we'll specialize the category of linear algebraic groups. Now, I don't have to unpack what all of this phrase means because we can think of them very concretely. So these are closed subgroups of some GLN of C. So we'll work over the complex numbers. The phrase makes sense over other fields, positive characteristic, it's algebraic geometry, but for our purposes, we can focus on the complex numbers. closed subgroups of GLNC, and the morphisms are basically polynomial. Group morphisms that are also expressible as polynomials, whose components are polynomials. So morphisms are polynomial polygroup morphisms. So things like the determinant. The determinant goes from GLN of C to C cross, which is GL1 of C. GL1 of C. This is the determinant. This would be an example. So they were looking to characterize epimorphisms in this category of linear algebraic groups. Now, notice something about this category. So this category, let's call it alg groups over C, is what I'm going to refer to as a concrete category. And again, it's not just me saying these words. They are in wide use. Is a concrete category.
There is a question in the chat. I don't know if you can see it.
I can see there's something, but I have to open this.
I can ask you the question.
Oh, okay. That will go.
Deb asks if are these closed subgroups also varieties?
Yeah, so closed was a little ambiguous. I mean, closed in the Zariski topology. So closed with respect to the topology that makes them algebraic varieties. Or if you want, I can say it like this. They are zeros of collections of polynomials. So they're closed in that strong sense. Yeah, and this also makes them algebraic varieties. So the answer is yes. The short answer is yes. And they're also smooth because we're complex, and this is automatic for group varieties. So they're very nice objects. And the category is concrete in the sense that its objects are sets with some additional structure, but they are at least sets. Objects are sets. Objects are sets. And the morphisms are functions. They are structure preserving functions. They're very special functions. They have to preserve the group structure. They have to preserve the algebraic variety structure. We just talked about that. But in any event, they are functions. And the morphisms are functions. Morphisms are functions. So now, sorry, I would trying to change position here so my chair doesn't topple over. So I was talking a big game about how you have to make sense of surjectivity in the abstract, because I want to talk about it in abstract categories. But these categories we'll be interested in are also concrete, in fact. So in these categories, because the objects are sets, so they do have points. We haven't gone non-commutative yet. This is still ordinary geometry. This is not non-commutative geometry yet. It's plain algebraic geometry. It isn't non-commutative algebraic geometry, if you'll pardon the double negation. So because these are also concrete categories, it does make sense to talk about surjectivity. So there are morphisms. There are morphisms in alg-GP-C that are surjective just as set maps. That's one class. Like this one. This one's surjective, right? For every non-zero complex number, there is some matrix whose determinant that complex number is. This is a surjective morphism. And there are epimorphisms, as there are in any category. This is a category, so I can talk about its epimorphisms. Epimorphisms. and I've shortened it to Epis, as I said I would. You always have this implication in concrete categories, sort of obviously, in any concrete category. And depending on your category, the converse may or may not be interesting. So the converse, I'm going to mark with a question mark. And this is usually an interesting question. Are epimorphisms surjective? Well, it's interesting depending on the category. In some categories, it's more interesting than in others. Interesting question, depending on the category. Depending on the category. On the concrete category. As soon as I can make sense of both notions, I can ask about this converse implication. Epimorphisms I can make sense of in full generality in any category. Surjectivity, no. I need sets, I need points, depending on the category. And so let me also state the question, is every, stated in words, is every, well, actually, start over, because this is shorter. Are epimorphisms surjective? And the answer is no in many cases. There's many people asking this over decades, right? So let me give you a sampling of examples. Maybe some results due to read. Actually, most of the affirmative ones that I'm going to mention, I think, are going to be due to read, and they go back to a single paper. If you search for Reed's name on like academic databases with for epimorphisms in the title, you'll find the paper. The answer is yes. The answer is yes in a number of categories. So for compact groups, the category of compact groups, not algebraic groups. You know, I've changed the setup a little. Compact groups. Also for C-star algebras, I know people like operator algebras in this crowd, for C-star algebras. Also, in fact, for von Neumann algebras, I'm going to call them W-star algebras. In fact, there are all sorts of connections coming out of straight out of just plain what we like to call category nonsense, abstract nonsense. So from sheer category theoretic nonsense, if you know the result for W-star algebras, you can get it pretty quickly for C-star algebras. So it's better to know it for von Neumann algebras. A number of other cases, semi-simple Lie algebras, semi-simple complex Lie algebras. That's a category, right? Semi-simple Lie algebras. Few other cases I want to mention. Now, a lot of the time, the answer is no. And also for interesting categories, interesting natural categories. In fact, let me go back to connect a circle here. Go back to Bien and Borel, where they characterize the epimorphisms in the category of linear algebraic groups. You just see directly from the characterization that the answer is no in that category. There are very natural, very interesting, very commonly occurring morphisms of linear algebraic groups. I'll give you very concrete examples in just a second, that are epimorphic, but not, absolutely not, surjective. So Bien Borel, for my notation was algp. Actually, their characterization works not just over C. I'm focusing over C. focusing on the complex numbers rather. An example of an epimorphic morphism, examples, it's a family of examples. An inclusion of Borel. I don't know if Bien-Borel were calling them Borel subgroups, but we call them Borel subgroups of a Borel subgroup of a semi-simple, for example, algebraic group. A more concrete example, a sub-example. So this is a whole family of inclusions that are epimorphic. Inclusions, not surjections, right? Sub-example. Upper triangular.
Another question in
Yeah.
the chat.
Yeah.
Is the result by Bien-Borel specific to algebraic groups over C, or is it true over any field?
It's true over any field. Their results are not just over C. But also, this is not the result. This is a specialization of the result. The result I will state a little later when we get to generalizations of it to non-commutative geometry. The example I've given you here follows from their work, but it's not their work itself. Their work is more general. So the sub-example would be unimodular, because I said semi-simple, so I have to look at the special linear group, because that's semi-simple. Unimodular, upper triangular matrices. This is a triangle. I'm not writing the word triangular, it's too long. Sitting inside SLN of C. That's a Borel, this is a Borel subgroup, and it sits inside here. Obviously, it's not the whole thing, right? Not all matrices are upper triangular, but the inclusion is epimorphic. Yeah, so there are very natural examples, but notice though, already you'll start seeing a pattern here that I might have time to sort of spell out a little better later. Here we had compact groups. Epimorphisms were surjective for compact groups. There's a connection between compact groups and linear algebraic groups. You can complexify every compact Lie group into a linear algebraic group, which is then going to be reductive automatically. Now, reductive groups are sort of at the opposite end of a spectrum from Borel, so from solvable groups. So, in a sense, epimorphisms tend to be surjective when there's some rigidity to the objects or some representation theoretic rigidity. The representation theory of compact groups is discrete. Everything breaks up as a sum of symbols. The same happens for semi-simple linear algebraic groups. And then you have these triangular ones that are sort of the opposite of that. They're very non-rigid in that sense. The representation theory is not semi-simple. You have many representations that have sub-representations that are not direct summands. So you start seeing these non-surjective epimorphic embeddings as soon as you get some non-rigidity to your representation theory. That's a general phenomenon that I can only state loosely at the moment. In fact, maybe just for the whole talk, I don't think I have time to expand too much on this, but that's a general pattern that pops up again and again and again in this business.
One question.
Yeah.
But you always see the semi-simplicity of the representation, is that right? The semi-simplicity is behind of that?
Yes, yeah, that's right. Yes.
Okay. So
You're going to see more of this when I state some more of the results. So semi-simplicity will play a crucial role in breaking these sorts of pathologies where you have non-surjective epimorphisms. So there's a strong link there. Did you want to follow up that with something?
No, I'm just thinking another question, but that's okay. Yeah.
Okay. All right, so these would be very natural examples. People talk about Borel subgroups all the time, and in fact, maybe the way they would have phrased it, since Borel was one of the co-authors, so they wouldn't have been talking about Borel subgroups, but it works more generally for parabolic subgroups. So those Borel can talk about without naming himself, right? So more generally, embeddings of parabolic subgroups, parabolic. Are epimorphic. Or I could have just said epic in algebra. They don't have to be semi-simple or anything like that. As soon as you're parabolic means this. Parabolic means, since we're talking about algebraic varieties, everything in sight is an algebraic variety, and you call a subgroup parabolic. If the quotient variety, which always exists, you can make sense of it by general nonsense on algebraic groups, if the quotient variety is a projective variety. Yeah. So if you do that for this example, SLN modulo triangular matrices, you get the flag variety, the variety of flags, which is a generalization of the Grassmannian, right? So those are projective varieties. They are closed algebraic, so also analytic subvarieties of projective space. Closed subvarieties of PC. So, right, so this follows from Bien and Borel. What Bien and Borel did was the following. So Bien and Borel, more specifically, let me try again. I keep uttering this word, characterize. They characterized the epimorphisms, meaning they don't just give some random examples. They tell us which ones they are by means of other properties. Obviously, there's a definition for being epimorphic, and then they give equivalent characterizations of that property. So in algebp, C, an embedding, and it's enough to talk about embeddings because that's where the interesting, that's where the crux of the matter is. An embedding is epimorphic if and only if. Now, there are a number of ways to say this. So maybe one, let's say A. I prefer letters for these sorts of enumerations of properties. One way to say it is that the invariant functions, so regular functions, it's polynomial functions on the algebraic variety, regular functions on G, invariant under H. Invariant under, let's say, left, but it works for right as well because you can flip on the other side taking inverses. H translation are scalar. So the only the obvious ones are invariant, are scalar. B, B says something like this. If I give you a G representation, so now there's some representation theoretic characterizations as well. This is how you make the connection to representation theory. Or for every representation, G representation V, and decomposition, direct sum decomposition, V isomorphic to V1 direct sum V2 over H. So if it decomposes like this after you've restricted it to H, comma, the decomposition already holds over G. So these are summands over G as well as H. You just knew to begin with that they were H summands, but they are in fact G summands as well. So this is a property of the embedding. The decomposition holds over G. The decomposition holds over G. C, it's also representation theoretic. For every G representation, V, comma, the H invariance, V and V, so that HV equals V for every H in H. And we write V upper H for that. And this is what it is by definition. The H invariants are in fact already G invariants. So if you're preserved by everybody in H, you're in fact preserved by everybody in G. Are in fact G invariant. Or also for representations, the restriction functor from representations of G to representations of H, the restriction functor is just the obvious one. You take a G representation and just restrict your attention to H. This functor is full, meaning that if I give you two G representations and the morphism between them that intertwines the operators from H, then in fact it already automatically intertwines the operators from G. I think they gave a couple more, but I'm going to stop here because why not? This is a good place to, it's enough. And now to follow up on something we were discussing above, is those examples with the parabolic subgroups. One way of restating condition A, it's the geometric one, the one that didn't talk about representations, is to say that the variety G mod H has only scalar global regular functions. Scalar global regular functions. Now, this happens, of course, this is the case if G mod H is projective. So if H is parabolic. This is a general fact about projective algebraic varieties. Connected projective algebraic varieties have only scalar global functions. i.e., if H is parabolic. So parabolic implies epimorphic. That's why I said those parabolic examples follow from the Bien-Borel results. The converse doesn't necessarily hold, but the examples are a little hard to give. I don't have them at my fingertips, so just take my word for the fact. I think they might give some examples that this doesn't hold the other way around. It does not, this is not true. So it's possible for this variety to not be projective necessarily, but still not have very many global regular functions. So projectivity is just sufficient for having few global functions. It's not necessary. Yeah, so far, any questions? Because I do want to tell you some maybe new theorems in the not so much time I have left. But I will forego that for questions. I prefer answering questions to tell you the theorems.
Yeah, I have a small question.
Okay.
Do you have the version for the coordinate algebra of the algebraic groups for that? For example, the first one means that you have a Hopf-Galois extension or something like that.
Yeah, when I tell you about Hopf algebras, I will give you
okay.
version of all of this. This is where we'll go. Yeah.
Okay. I'll wait for it then.
Okay. Other questions? Okay, so then let's go to Hopf algebras then. So non-commutative NC geometric version of Bien-Borel. And actually, it's not just an NC version. It implies Bien-Borel's result, because everything I just told you about algebraic groups, you can rephrase in the language of commutative Hopf algebras. The category of commutative Hopf algebras is contravariantly equivalent to the category of linear algebraic groups. So everything I was saying about G representations, I can say about comodules over the Hopf algebra corresponding to G, and so on. Okay? And what you know about Hopf algebras, you can specialize to commutative Hopf algebras. So if you prove a version of Bien-Borel for arbitrary Hopf algebras, you'll be able to specialize. Okay, so this is not just a version, it's a generalization of Bien-Borel. So we will be working in the category of Hopf algebras over some field. I don't even care what the field is. The category is, I'm going to call it H-alg, if I can spell it, H-alg. I guess the answer is I can't spell it. Over some fields that I'm going to fix, but then ignore. Fixed over a fixed field. It is a field. There are some issues over commutative rings and so on, and maybe we ignore those for good. Over a fixed field. Now you have to be careful. I can't talk about epimorphisms in the category of Hopf algebras, because the category of Hopf algebras should be contravariantly equivalent to the category of linear algebraic quantum groups. That's what we mean by quantum groups, really. uh, contravariant. So when I told you about epimorphisms in here, I meant to analogize BB, Bien-Borel, I need to talk about epimorphisms in this category that I'm highlighting here. To move to this other category, I move contravariantly, so I need to reverse arrows. So in here, I need the notion dual to that of epimorphism. That's what monos are. Monomorphisms are the dual notion to epimorphisms. So we talk about epis here and we talk about monos there. That's the monos of the talk's title. So now we've touched on that as well. A monomorphism, now let's call them H because they're Hopf algebras. A monomorphism from H to H prime, let's call it M. M is monic or a monomorphism. Monic if for every two distinct arrows, F different from G, landing into H. So the picture looks like this. MF is different from MG, comma, M composed with F is still different from M composed with G. That's what monic means in any category. This is again a purely, this thing I'm showing you now on my page, because I've centered the screen, is a purely category theoretic notion. And this is what we're interested in the category of Hopf algebras, monomorphisms, because those correspond to epimorphisms of linear algebraic quantum groups. So here's a theorem. This, as far as I know, is due to me. But it's very easy to prove. So, you know, that's not saying much. So a morphism, or let's say a surjection, because those are the interesting ones. A surjection H to H prime, let's call it M, of Hopf algebras. Is monic if and only if. And now let's go through the conditions, A, B, C, and D. And they will be precise analogs, including an answer to the question I was just asked, right? Here's what A looks like at the level of Hopf algebras. You simply tell me that if you take H and consider the H prime coinvariants, those are just the scalars. Now, here's what I mean by H prime coinvariants. These are the elements of H such that if I first apply the co-multiplication of the Hopf algebra, H1 tensor H2, and then I apply my morphism on one tensorand, I just get the stupid coaction by the scalars. H tensor 1. This is what is meant. This is the definition of the coinvariance. That's my notation for this. So the circled thing is notation for that set. Yeah? If you translate it back to algebraic groups and thinking through it as you do it, you'll get exactly condition A from Bien-Borel. So this is the answer to that question. So it's much simpler than Galois. There's nothing about Hopf Galois stuff here. B says that, so these are just straight up lifts from Bien-Borel. For every finite dimensional comodule, FDH comodule, V, and splitting V isomorphic to V1 direct sum V2 as H prime comodules.
I have a question.
Yeah.
Could you visit condition A again? Yeah. So it says H1 tensor M of H2 equals H tensor 1.
Yeah.
There is, well, there's an H1 and an H2 on the left-hand side, and there's none on the right-hand side.
Right, but that's fine. So the notation looks like maybe not everybody is familiar with this. So H comes equipped with this co-multiplication thing, and it's very common to write it as H going to H1 tensor H2.
I see. Okay.
So that's what that is. So there's a hidden summation symbol. That's what I meant by that. Yeah, sorry.
Sure.
We call this Sweedler notation. It's shorthand. It can be confusing at first. So that's what
okay.
Yeah. So actually, this comes out of H. H1 and H2 depend on H. So it's all an equation involving H. Yeah.
Okay. Thanks.
Okay. Great. Thanks for that. That's it's sort of I slid that under the rug. Every splitting of H prime comodules is in fact a splitting of H comodules. The splitting is one of H comodules. C says that for every H comodule V, you can also ask this just for finite dimensional ones, it doesn't matter. You get an equivalent condition, comma, the H prime coinvariants, they're defined similarly to these guys. In fact, it's exactly the same, except you take elements from V instead of elements from H. Are also, in fact, H coinvariants. And finally, D says that I guess you can call it restriction again. Sometimes people call it co-restriction because you dualized your picture a little bit. The co-restriction functor from H comodules to H prime comodules is full. And then there are more conditions to this. So there's an E and there's an F and so on. Actually, I can't remember how many. So these have to do with involving pullbacks in the category of Hopf algebras, which are things that exist, but that you don't encounter all that often. And similar universal constructions. Universal constructions. And all of this specializes back. So it's a fact. It's a fact that if I give you a morphism of commutative Hopf algebras, it's monic. Now, monic is ambiguous. We talk about monos in a specific category. This is a morphism in the category of Hopf algebras. It's also a morphism in the category of commutative Hopf algebras. But the point of this sentence I want to finish, and then I'm done, is that it doesn't matter. They're monic simultaneously or not. So it's monic in H-alg if and only if it's monic in H-alg commutative. So one recovers, so this is also dual to linear algebraic groups. So you recover Bien-Borel from the above. Yeah, because if you know a characterization in here, you know a characterization in the commutative subcategory as well. So you get back exactly what you have. And I think I'm done. Just a minute over time, for which I apologize. This is it.
Okay, thank you very much, Alexandru.
Mm-hmm.
Is there any question?
Yes, I have one.
Yes.
First, thank you very much, Alexandru, for a very nice talk. One question about the functor, the restriction functor.
Mm-hmm.
How far is it to be an equivalent? I'm thinking in cocycle deformation of things. If you have a morphism like this, it might be monic, but then it means that when you have a cocycle deformation, the category of comodules are equivalent.
Right. So now these are slightly different settings. And of course, if I give you just two Hopf algebras,
yeah,
in many cases of interest, you have equivalencies between their categories of comodules.
Yeah.
That don't come out of morphisms. As you said, they might be cocycle deformations, or they might be stranger bigallo objects that put in correspondence on the two sides comodules of different dimensions. So they're worse even than cocycle deformations.
Yes.
But my functor that I was talking about came out of a morphism. And in that setting, it is known that the morphism of Hopf algebras is a bijection if and only if the functor is an equivalence. So if I give you a morphism of Hopf algebras, you already have the morphism. Then the morphism is bijective if and only if the corresponding co-restriction functor is an equivalence. So in the setting of the theorem, they're as far as it gets. I mean, you know, you cannot be an equivalence without being an isomorphism.
Okay.
Yeah.
Okay. Any other question?
I have a general question. In the world of groups, you can talk about simplicial resolutions of groups using epimorphisms. So you take the free group of a group, and that comes with an epimorphism to the group. Can you do this in this quantum group world as well?
I certainly haven't seen this sort of thing done. But in what sense is it an epimorphism? I don't even know that I'm familiar with the classical context.
I couldn't hear your question. Could you repeat that?
I don't even think I'm familiar with the classical context that you're talking about. What sorts of epimorphisms do you get? Epimorphisms that are not surjections?
No, these are surjections.
Right, yeah. So, well, I mean, surjections you can always generalize for quantum groups, right? They would be just embeddings of Hopf algebras.
Okay.
So those are not very interesting. Yeah.
Right.
I should have said epimorphisms because it sounded like you were talking about discrete groups. Epimorphisms of discrete groups are automatically surjective. So we were back in the good old familiar setting where, you know, everything makes sense epimorphisms are surjective, monomorphisms are injective, and so on. So sure, for in the quantum setting, a quotient quantum group would be an embedding of Hopf algebras, I suppose, is how I would define
it. Okay. So, Alexandru, what do you mean by quantum group, an algebraic quantum group?
For the purpose of my talk, I meant what I defined it to be. So let me go back. There it is. I have defined the phrase linear algebraic quantum group by this equivalence.
Okay.
If the category of Hopf algebras form its dual, that's the category of linear algebraic quantum groups. That's it.
Okay.
So it's the category opposite to Hopf algebras is what I meant by it.
Okay.
And sometimes people mean variations of this. Sometimes they focus only on Hopf algebras with bijective antipode. There's versions of this. But for this talk, this is what I meant.
Okay, thank you.
Just to follow up on my previous question. So if you take a Hopf algebra, is there a free object in this category?
There's a free object. It depends on what. You can, not on a set, not quite on a set. It doesn't work that way. The forgetful functor from Hopf algebras to just sets, that's a forgetful functor. That's not a left adjoint. So there's not a free object in that sense. But there's a free object on a coalgebra. So if you forget from Hopf algebras to coalgebras, there's a left adjoint to that. That's the best I can do for a free object. And in fact, it's what you ought to mean by free objects. Because in this quantum business, a quantum set should be something like a coalgebra, maybe. Maybe. I'm not sure. I'm not sure. But in any event, that's one version of a free object. There are free Hopf algebras and coalgebras.
Okay, thanks. I have a question. I'm not sure what I'm going to ask. Maybe it's an intuitive question. Does it mean, with your result, does it mean that it's very difficult to have a categorical notion of quantum subgroup? You have kind of problem with Epis.
Yeah, that's right. Quantum subgroup is not necessarily easy to define. That's correct. I mean, one version you'll encounter often is just that of a quotient Hopf algebra. But
yeah,
of course, maybe that's not always what you mean. For some purposes, for instance, for the purpose of generalizing things like symmetric pairs. You know, in the classical world, people like to work with symmetric pairs, and those are certain kinds of embeddings of algebraic groups into other algebraic groups, or Lie groups into other Lie groups. For those purposes, quotient Hopf algebras are not general enough. So then maybe you want to talk about something like quotient left module coalgebra, or something like that. So yeah, there are versions of what you might mean by a quantum group, and it's not always clear what it should mean. But I don't know that that necessarily flows out of this epimorphism business, because you already have the issue of epimorphisms versus surjections for classical algebraic groups. So these are maybe parallel issues, but not necessarily. I wouldn't say that one implies the other.
Yeah, but it's not.
But I acknowledge that there's a problem with defining quantum subgroup.
It's not right to. I mean, it's very difficult to define a quantum subgroup in a categorical sense. So a quantum subgroup is an epimorphic image, an object in this category or something like that. It's not right.
Mm-hmm.
Okay. Any other question? Well, if not, thank you again, Alexandru, for the nice talk.
Thank you, and thanks for all of the questions. That's how you know people paid attention.
Yes. Okay. Thank you very much.
All right.
Well, now we can stop the recording.